In abstract algebra, field extensions are the main object of study in field theory. The general idea is to start with the base field and construct in some manner a larger field that contains the base field and satisfies additional properties. For instance, the set Q equals a plus b square root 2 a, b. Q is the smallest extension of Q that includes every real solution to the equation x2 equals 2. Definitions. Let L be a field. A subfield of L is a subset K of L that is closed under the field operations of L and undertaking inverses in L. In other words, K is a field with respect to the field operations inherited from L. The larger field L is then said to be an extension field of K. To simplify notation and terminology, one says that L, K is a field extension to signify that L is an extension field of K. If L is an extension of F which is in turn an extension of K, then F is said to be an intermediate field of the field extension L, K. Given a field extension L, K and a subset S of L, the smallest subfield of L which contains K and S is denoted by K, i.e., K is the field generated by adjoining the elements of S to K. If S consists of only one element S, K is a shorthand for K. A field extension of the form L equals K is called a simple extension and S is called a primitive element of the extension. Given a field extension L, K, the larger field L can be considered as a vector space over K. The elements of L are the vectors, and the elements of K are the scalars, with vector addition and scalar multiplication obtained from the corresponding field operations. The dimension of this vector space is called the degree of the extension and is denoted by L, K. An extension of degree 1 is called a trivial extension. Extensions of degree 2 and 3 are called quadratic extensions and cubic extensions, respectively. Depending on whether the degree is finite or infinite, the extension is called a finite extension or infinite extension. Caveats. The notation L, K is purely formal and does not imply the formation of a quotient ring or quotient group or any other kind of division. Instead, the slash expresses the word over. In some literature, the notation L, K is used. It is often desirable to talk about field extensions in situations where the small field is not actually contained in the larger one, but is naturally embedded. For this purpose, one abstractly defines a field extension as an injective ring homomorphism between two fields. Every non-zero ring homomorphism between fields is injective because fields do not possess non-trivial proper ideals. So field extensions are precisely the morphisms in the category of fields. Henceforth, we will suppress the injective homomorphism and assume that we are dealing with actual subfields. Examples. The field of complex numbers C is an extension field of the field of real numbers R, and R in turn is an extension field of the field of rational numbers Q. Clearly then, C, Q is also a field extension. We have C, R equals 2 because 1, I, is a basis, so the extension C, R is finite. This is a simple extension because C equals R, so this extension is infinite. The set Q equals a plus b square root 2 a, b. Q is an extension field of Q, also clearly a simple extension. The degree is 2 because 1 square root 2 can serve as a basis. Q equals a plus b square root 3 a, b. Q equals a plus b square root 2 plus c square root 3 plus d square root 6 a, b, c. dq is an extension field of both Q and Q, of degree 2 and 4 respectively. Finite extensions of Q are also called algebraic number fields and are important in number theory. Another extension field of the rationals, quite different in flavor, is the field of p-adic numbers Qp for a prime number p. It is common to construct an extension field of a given field K as a quotient ring of the polynomial ring K, X, in order to create a root for a given polynomial f. Suppose for instance that K does not contain any element x with x2 equals -1. Then the polynomial x2 plus 1 is irreducible in K, x. Consequently the ideal generated by this polynomial is maximal, and L equals K, x, is an extension field of K which does contain an element whose square is -1. By iterating the above construction, one can construct a splitting field of any polynomial from K, x. This is an extension field L of K in which the given polynomial splits into a product of linear factors. If P is any prime number and n is a positive integer, we have a finite field GF with Pn elements. This is an extension field of the finite field GF equals ZPZ with P elements. Given a field K, we can consider the field K of all rational functions in the variable x with coefficients in K. The elements of K are fractions of two polynomials over K, and indeed K is the field of fractions of the polynomial ring K, x. This field of rational functions is an extension field of K. This extension is infinite. Given a Riemann surface M, the set of all meromorphic functions defined on M is a field, denoted by C. It is an extension field of C, if we identify every complex number with the corresponding constant function defined on M. Given an algebraic variety V over some field K, then the function field of V, consisting of the rational functions defined on V and denoted by K, is an extension field of K. Elementary properties. If L, K is a field extension, then L and K share the same 0 and the same 1. The additive group is a subgroup of, and the multiplicative group is a subgroup of. In particular, if X is an element of K, then its additive inverse minus X computed in K is the same as the additive inverse of X computed in L. The same is true for multiplicative inverses of non-zero elements of K. In particular then, the characteristics of L and K are the same. Algebraic and transcendental elements and extensions. If L is an extension of K, then an element of L which is a root of a non-zero polynomial over K is said to be algebraic over K. Elements that are not algebraic are called transcendental. For example, in C, R, I is algebraic because it is a root of x2 plus 1. In R, Q, square root 2 plus square root 3 is algebraic, because it is a root of x4 minus 10 by 2 plus 1. In R, Q, E is transcendental because there is no polynomial with rational coefficients that has E as a root. In C, R, E is algebraic because it is the root of x minus E. The special case of C, Q is especially important, and the names algebraic number and transcendental number are used to describe the complex numbers that are algebraic and transcendental over Q. If every element of L is algebraic over K, then the extension L, K is said to be an algebraic extension, otherwise it is said to be a transcendental extension. A subset S of L is called algebraically independent over K if no non-trivial polynomial relation with coefficients in K exists among the elements of S. The largest cardinality of an algebraically independent set is called the transcendence degree of L, K. It is always possible to find a set S, algebraically independent over K, such that L, K is algebraic. Such a set S is called a transcendence basis of L, K. All transcendence bases have the same cardinality, equal to the transcendence degree of the extension. An extension L, K is said to be purely transcendental if and only if there exists a transcendence basis S of L, K such that L equals K. Such an extension has the property that all elements of L except those of K are transcendental over K, but, however, there are extensions with this property which are not purely transcendental. A class of such extensions take the form L, K where both L and K are algebraically closed. In addition, if L, K is purely transcendental and S is a transcendence basis of the extension, it doesn't necessarily follow that L equals K, Q, where X is transcendental over Q. The set X is algebraically independent since X is transcendental. Obviously, the extension Q is algebraic, hence X is a transcendence basis. It doesn't generate the whole extension because there is no polynomial expression in X for square root X. But it is easy to see that square root X is a transcendence basis that generates Q. So this extension is indeed purely transcendental. It can be shown that an extension is algebraic if and only if it is the union of its finite sub-extensions. In particular, every finite extension is algebraic. For example, C, R and Q, being finite, are algebraic. R, Q is transcendental, although not purely transcendental. K is purely transcendental. A simple extension is finite if generated by an algebraic element, and purely transcendental if generated by a transcendental element. So R, Q is not simple, as it is neither finite nor purely transcendental. Every field K has an algebraic closure. This is essentially the largest extension field of K, which is algebraic over K and which contains all roots of all polynomial equations with coefficients in K. For example, C is the algebraic closure of R, normal, separable and Galois extensions. An algebraic extension L, K is called normal if every irreducible polynomial in K, X, that has a root in L completely factors into linear factors over L. Every algebraic extension F, K admits a normal closure L, which is an extension field of F such that L, K is normal and which is minimal with this property. An algebraic extension L, K is called separable if the minimal polynomial of every element of L over K is separable, i.e., has no repeated roots in an algebraic closure over K. A Galois extension is a field extension that is both normal and separable. A consequence of the primitive element theorem states that every finite separable extension has a primitive element. Given any field extension L, K, we can consider its automorphism group AUT, consisting of all field automorphisms alpha. LL with alpha equals X for all X in K. When the extension is Galois, this automorphism group is called the Galois group of the extension. Extensions whose Galois group is abelian are called abelian extensions. For a given field extension L, K, one is often interested in the intermediate fields F. The significance of Galois extensions and Galois groups is that they allow a complete description of the intermediate fields. There is a bijection between the intermediate fields and the subgroups of the Galois group, described by the fundamental theorem of Galois theory. Generalizations. Field extensions can be generalized to ring extensions which consist of a ring and one of its subrings. A closer non-commutative analog are central simple algebras, ring extensions over a field, which are simple algebra and where the center of the ring is exactly the field. For example, the only finite field extension of the real numbers is the complex numbers, while the quaternions are a central simple algebra over the rails, and all CSAs over the rails are equivalent to the rails or the quaternions. CSAs can be further generalized to Azuma-U algebras, where the base field is replaced by a commutative local ring extension of scalars. Given a field extension, one can extend scalars on associated algebraic objects. For example, given a real vector space, one can produce a complex vector space via complexification. In addition to vector spaces, one can perform extension of scalars for associative algebras defined over the field, such as polynomials or group algebras and the associated group representations. Extension of scalars of polynomials is often used implicitly, by just considering the coefficients as being elements of a larger field, but may also be considered more formally Extension of scalars has numerous applications, as discussed in Extension of Scalars. Applications.